In this video, I will show you how to implement a discrete time implementation of a first order filter or first order system. This example is readily available on the web page dedicated to the course, as you can see over here. If you download the zip file and then unzip it, and then go to Matlab and to the corresponding folder, this is what you obtain. Do not bother about the two PNG files. They are there to explain you how to set the sampling time for the Matlab function, but this will be explained later in the video. Well, if you click on this SLX file, this is a Simulink file, you can open the discrete implementation of the first order system. This is the first order implementation, right? This is the input. As you can see, the input can be a vector signal. Here the vector signal contains, well, at the first input a step and the second input is a ramp. So obviously at the output you'll have also a vector with two outputs, the step response and the ramp response. This first order system comes with a faceplate. You have to double click and here you have it. As you can see, we implement here a discrete first order system using the Euler backward difference approximation method that we have seen in the theoretical part of the course. There are three parameters: the sampling period TS expressed in seconds, the gain of the first order system, and the associated time constant. It's a lag time constant and it's obviously also expressed in seconds. Well, we can now run the system by pushing on this green button and look at the output. So over here we obtain indeed the step response of a first order system. Remember that the first input is a step and we had a time constant of 10 seconds. So we should obtain a steady state after roughly 5 times the time constant, so 50 seconds, and as you can see, this is, well, the case. The second output here is the response to a ramp, and this is how it looks like. You can also see here that the static gain of the first order system is 1. We have here a unit step at the input, and you can see that in steady state, when t tends to infinity, the response of the first order system tends to 1 as well. So indeed a static gain of 1. And by the way, the ramp here at the input is not a unit ramp, it's a ramp with a slope of 0.1 per second. So what we can do now is zoom in and have a look at the step size, and as you can see here you have 0.2 seconds and you have, well, 4 sampling instances. So indeed the sampling periods is 0.05 seconds, and this is also the case for the ramp response, as you can see. What we can do is change the sampling period, for instance, to 1 second and have a look at the response. And this is what you see. This is indeed the same kind of response as obtained earlier, but you can clearly see now that the sampling period has been increased. What we'll do next is to implement this first order system in Simulink, but from scratch. This is very important that you can do this because you'll have to do something similar for a lead lag system that will be used in your feed forward and for a PID controller. Remember that when you have implemented your block, you should test it before using it in your controller and your feed forward. As you can see, I have deleted everything here and will now start from scratch to construct this discrete implementation of a first order system. So you start by right clicking, new, and then you take model. And this will create an SLX Simulink file and we'll call it first order. And then you can simply open it. Well, the first thing that you have to open is the library browser, and then you go to user defined functions, and then you'll find Matlab function, right? We'll implement our first order system using a Matlab function, and we'll call it first order. And then we click, and here you see that you have code, so we'll remove this. And we'll prepare our function. The output will be out, the input is in, and of course we have parameters. Remember that we have the sampling period, we have the gain kp, right, and we have the lag time constant. We'll do it like this, right? And then we can return to our block, and you can see now that our Matlab function has an input, an output, and 3 parameters. If we go back to the library browser, we can go to sources. Well, the first input here is really an input. We'll do like this, and if we go back to sources, well, these ones here are constants, right? So this is TS. It's in red because TS is not known. We'll see how we can deal with that later, right? So this will be the gain KP, and we'll have here T lag. Right, and now we have also an output. You go to sinks, and this is really an output of the block. So in this way, everything is ready to mask the block. As usual, it's good to save once in a while. So what we'll do now is select everything and then right click and then go to create subsystem from selection, and here you have now a block which we'll call also first order, right? And if you click, well, you see what is below, right? So this is a subsystem. So if you click on this block, you can go to mask and create mask. This is going to create this, well, faceplate that we've seen earlier, right? So what we'll do is create the parameters. As you can see here, we have an input, an output, right? Actually, we do not need these inputs and outputs anymore, because later on we'll connect a step here and we'll put a scope, right? So let's go again to this mask, and what we can do is create the parameters. So you push over here and you can have a first parameter. Remember that the first parameter was the sampling period, TS, and it's good to be precise, right? So it's in seconds, right? So what you have to do here is give a name, and here it will be TS. This is the name of the variable below the mask, and we can give it an initial value in the faceplate 0.05. If we do this and we close, what will happen if we click now over here, we have sampling period TS 0.05, right? And well, this variable is known as TS. As you see, it's no longer red over here. It's known below the mask. And of course, what we should do is do this for every parameter, well, the gain of the system and the lag time constant. I'm going to do this now. As you can see, I've added the two other parameters, the gain KP and the time constant T lag. These are the variables that are used beneath the mask, right? And you can see that I've given initial value here for KP and for T lag. So if we now look in the faceplate, this is what you have here. You have the initial values. Of course, you can change them later if you want to. And if you go and look beneath the mask, you can see that TSKP and TLAG have now variables, values 0.05, 1, and 10. Of course, it's always good to add a little bit of documentation, so you can go to the documentation tab and type, well, discrete first order, right? And it's Euler backward difference approximation method that we will be using. And if you apply and if you click now on the mask, you can see this appearing over here. So it's good to save again. Now the faceplate is ready and we can adjust everything that is below the faceplate. For instance, you can adjust the name of the input and the output. And then, very important, this is going to implement the recurrent equation for the first order system, and this equation should run every TS. So what you should do is right click on the block, go to block parameters and set the sampling time to TS to ensure that this block will run every TS. This is really important. What we'll do here is implement the Euler backward difference approximation for a first order system with this transfer function, right? And what we'll have to implement is this recurrent equation. If this equation comes as a mystery to you, you should probably go back to the theoretical course. So what we need over here is to keep track of the previous output. So we'll have to keep it into memory, and we need to define a constant k, right, which is the sampling period over the time constant of the first order system. Once we have done this, all we have to do is implement this recurrent equation. Well, let us implement this discrete recurrent equation. So again, we'll save, we'll go to the function, and this is, well, the code that we have here. Everything here is underlined because these inputs and parameters are not used yet. So to implement our recurrent equation, this is what we need. So this persistent out P stands for previous, well, keeps in memory the previous value of the output. Remember that this code will be executed, well, every TS. So here we have the previous value of the output. It's always good to put a comment here to tell you, well, which approximation here is used, and here it's the Euler backward difference, and we can put difference over here. Then we define the parameter k, which is TS over T lag, and here you see the recurrent equation that I've shown you in the slide, right? It's important to pay attention and to put a parenthesis over here and over here, right? So this is the output. It's constructed from the previous output, and it's constructed from the input. And once the output is constructed, well, you set the variable out previous, right, to out, so that at the next iteration, well, the value is available for the next computation of out. Well, the code is nearly ready. The problem now is that at the first iteration, right, out P is not defined. So what we should do is add this code here over here. If out P is empty, well, then you define it, right? Well, there are multiple ways to define it. Well, this initialization of out P has the advantage that the output is directly initialized at its steady state output, so it will not start from 0. So this is an advantage. And also out P here is initialized at the same dimensions as in, right? If in is a vector with 2 elements, this will also be the case for out P, and therefore also out, right? So this is the way to go, and this implements a first order system using recurrent equations. And as you can see, you only need a few lines of code. So let's save this and let's close this, right? And we are now ready with our first order block. All we need to do is test it, of course, before we start to use it. Well, as you remember, we have tested our block with inputs a step. So here is the step, right? And we also use a ramp. So here is the ramp. So what we'll do now is create a vector signal. So you go to ports and subsystems. Now it's routing, signal routing, and you have here a mux, right? So this will create a signal, a vector signal. The first one, the first component will be the step input, and the second component will be the ramp. And here we have to set the slope to 0.1 per second. So we have now our input. Well, we can now look at the outputs. So we'll go to sinks because we need a scope over here, right? And we'll go to signal routing again to obtain a demux, right? The idea is to take the vector signal and to obtain 2 output signals. Then we click on scope and we have to define, well, 2 inputs. Well, this is in black. This is always nice to go to style and to, well, put everything with a background in white, right? So if you do this, this is what you obtain. And well, also what you can do is choose the color and also choose the line thickness, so we'll make everything a little bit, well, thicker, right? So what you can do now is connect this one with this one over here and this one with this one, so everything is right now for the output. So again, we should save, and we are now ready to run this Simulink file. Let's have a look. You can see that the 2 responses are on the same plot. This we can solve by going to layout and taking, well, 2 output plots. The colors are different, so if you want to give them the same color, you go to style, you can change the color here, and again we can take this thickness of 2, right? So here we ran for 10 seconds, but Well, we can see here that the time constant is 10 seconds. We need to go to 50. So this we can arrange over here and type 50, right? We save and then we can run it again. And this is what we had obtained earlier. So now we only see the outputs on the scope. So what we might do is put the inputs as well. So what we'll do is remove those two links. So we now need vectors at each input. So we'll use this mux over here. Control C, Control V, right? And we'll need another one over here, right? So the first output goes to here, the second output to here. We'll take the output of the step, so we go here, right click up to there, and here right click up to there, and we connect this to the scope, right? So if we run this now, this is what we have here. In the blue the input and in red the output. So what you can do is make this second line a little bit thicker. So this is the step, first display the step. So if we take the other one, we have this one, we can change color and give it a thickness of 2. If we now go to the second display, well, we have red again. Let's change this to green and give it a line thickness of 2. Okay, and this is what we have now. And again, we'll save. What can be interesting is to link a Simulink model to an M file or an MLX file in Matlab. So let's do this. So I'll take an M file, so we'll call it variables first order, right? And then what we can do is define TS as 0.05, right? KP as 1 and T lag as 10. Then we can save this, right? And we can make the link with Simulink as follows. So you go to modeling, model properties, and then you have here callbacks, preload, and then you type variables first order. Let's have a look at how, yeah, this was variables. So, and you do not need to use the extension .m, and then you apply, okay, and of course as usual you save. The advantage is now that when you restart Matlab and you launch your Simulink file, you will launch this M file as well, and then in your first order block you can make the links with the variables that are in the workspace. As you can see, it's in red because these variables are not available yet. Okay, so this is why this is appearing in red. When you see something appearing in red, it means that the variables are not available. And now if we execute this M file, as you can see here, now the variables are available and we'll be able to launch our Simulink file. And as you can see, this is disappearing, and of course this is producing the same result, right? So the advantage is now that when you close everything and you clear all variables, as you can see, it has disappeared. And now if you open this file, this is taking a while. This is kind of normal. You see the file opening, and as you can see over here, the variables are available again. So it's very easy to work in an M file, a separate M file or MLX file, where you put all the variables and you do your computations, right? And you make the link with your Simulink file as I have just shown.